Hi everybody. Today in this lecture I'm going to be walking you through chapter 15 of Living in the Environment, which is going to examine non-renewable energy sources. We're going to look at petroleum products, we're going to look at natural gas, and we're going to look at coal. Also, uranium and other radioactive materials are in non-renewable energy. A lot of students ask me why that is because nuclear power is and can be a viable alternative energy source other than fossil fuels. But the reason it's in this chapter is that it is a non-renewable resource. In other words, once we use the radioactive material, it can't be replenished or renewed in a typical lifetime, right, or a typical life cycle. So it's considered to be a non-renewable resource, which is why it's in this chapter. We have to understand the concept of net energy in order to understand the efficiency and the ease with which we can use all of these energy resources. Net energy refers to the total amount of useful energy available from a particular resource, minus the energy needed to make it available to consumers, and that can include the mining of it, the extraction of it, the refining of it, the transportation of it, etc., in order to get that energy to consumers. And so we express our understanding of a particular resource's net energy as the net energy ratio, and we're going to think about the efficiency of these resources in these terms as we go through and learn about each of them. We'll say, yeah, this has a really high net energy ratio, or this has a really low net energy ratio. Resources with low or negative net energy yields kind of need help to compete in the marketplace, but they are out there. And if you have net energy ratio that you don't like, you can reduce the amount of waste that's produced from your particular resource, increase the efficiency of the extraction process for your resource, increase efficiency of how it's transported, captured, etc., whatever it is, in order to improve that ratio. I put this up every year because every year the EIA, the Energy Information Administration in the United States, updates their basic energy usage or consumption by resource here in the United States. And so we need to meet a total of about 100 quadrillion BTUs in order to power our country. And we've seen a reduction in the amount of coal used to do that here in the United States over the last few years. We'll see that on a timeline in just a second. We do have some nuclear electrical power that is generated, but for the most part we still use a large amount of petroleum and now use a large amount of natural gas. The renewable energy sector makes up about 11% of what we've got. And basically, it's divided up amongst biomass usage, either direct wood or biofuels, and then things like wind, hydroelectric, solar, geothermal, etc. We're going to look at those renewable sources in the next chapter. So for now, we're just going to focus on coal, petroleum, natural gas, and nuclear power. And we can look at sort of energy consumption in the United States over the course of basically the entire history of the country. At first, we primarily relied on biomass and had to do a fair amount of deforestation to meet the needs of the country as it was growing throughout the Industrial Revolution. Coal obviously became very, very important throughout the Industrial Revolution to power pretty much everything. For a while, coal was fairly dominant. We started extracting petroleum and oil products in the early 1900s and using that to power a significant amount of the United States. But we also started damming in the early 20th century and using some hydroelectric power. After the World War II era, nuclear came online, and in the 50s we started to see nuclear power being used. And then sort of the latest trend is that other renewable resources like solar and wind are being invested in. And we've had some ups and downs of petroleum use that sort of match natural gas use, and we'll talk about the reasons for that. And then we're seeing sort of a general drop off of coal as those other renewable energies come online. So oil is very important. It supplies a third of the commercial energy for the world. This 40% value is actually not accurate anymore, right? It's more like 37%. So we've dropped in the amount of oil that we're using. And I want to sort of talk to you about the types of petroleum that are out there and how we get them. Petroleum refers to what we call crude oil. This is a thick, liquidy material that's made up of a bunch of different combustible hydrocarbons, but it does have a fair amount of impurities in them. But it's liquid and found in fairly large quantities in the places where we have oil reserves. So it can be pumped up with some basic pumping technology, much like we use to pump water. It has a very high net energy ratio. Conventional oil, or sweet crude as we refer to it, has a better net energy ratio than almost any fossil fuel product, except maybe coal. But that requires really good oil, oils that don't have a lot of extra impurities like sulfur materials, etc. Unconventional heavy oil, which we do extract, is a little bit more difficult. It has a higher net energy ratio, and it requires more energy to pump it and extract it and refine it than you would get out of it comparatively to conventional or sweet crude. When an oil well starts to decline, we say that it has passed what we call peak production. And basically, you want to know how much a particular location that you're pumping is going to produce. And so we only are basically aware of a few proven oil reserves, but we assume that there's a bunch of unproven reserves still out there. We're still studying this, we're still exploring this. If you ever go into geology, the oil industry would love to employ you, because that idea of unproven reserves out there is a pretty big mystery for us. We have to assume that there is more oil, but we don't know that for a fact. The impurities in oil require a fair amount of refining to remove, but we use them for other purposes. So petrochemical is any product that comes from the oil distillation or refining process that's used to make a product. Plastics are a really good example of that. Synthetic fibers, or even non-cotton and wool fibers, like nylon, polyester, etc., tend to be a petrochemical base. A lot of paints, and even things like pesticides and other chemicals come from petrochemical original material. So we use a lot of what we pump when we use oil, when we get oil, but it comes at, some costs, right? Most of the proven oil in the world is held within these 13 countries. They make up what we call the Organization of Petroleum Exporting Countries, OPEC. They hold 60% of the world's proven oil reserves. Saudi Arabia has the largest proven reserve in the world, and they conduct the most conventional oil plumbing. OPEC has a fair amount of control over world markets, because they basically control when they release oil by the barrel to the world market. And so by having that ability to release more or less barrels of oil, they control the supply of oil and thus can control the prices, no matter what sort of the global demand is for oil at any given time. This obviously affects the price of additional goods and services that rely on oil and gas, the transportation of products, gas for consumer use, etc., are all going to be basically subject to whatever OPEC wants to do on the global scale. Um, and I'll talk about this in just a second, but one of the sort of biggest power plays that OPEC has done in the last, say, 15 years was to respond to proven reserves of other sources of oil, including shale oils and tar sands oils, which I'll talk about in just a moment. A shift to natural gas usage, like we have here in North America. And then, countries' use of other things like coal or shift to renewable resources. So there's a lot of politics and a lot of economics that come into play when we're thinking about the cost and the usage of these materials. The United States right now uses more oil than it produces. Last year, in 2019, we were using about 19.25 million barrels per day, that's how much we produced as a country, and we were consuming more than that. So we do rely on and we do require inputs of oil from OPEC, but we have shifted our focus to try and find other resources other than conventional crude oil. This kind of talks about or shows the price of gas over about 15 years. In 2008, gas went up to one of its highest points, as well as in 2012, and it's come back up. So we're back to that same price, roughly. But the cost of oil is increasing, is going to drive the cost of these other products because of the amount of production or transportation associated with those products. And it can even shift the price of electricity as well. So why would we want to keep using it? Well, we know we have some proven reserves that will last for decades. So it's there. It has a high energy yield. That's great. But the energy yield is decreasing as resources or reserves run out. We start to have to pump in different ways. Because it's a pump and drill system, there's a fairly low amount of land disruption at the surface. And we already have a really efficient distribution system that has been established throughout the 20th century. What are some disadvantages of oil? Unsurprisingly, we see a fair amount of oil spills and leaks from transporting it, and also from the extraction process itself. Deepwater Horizon and the Gulf oil spill is one of the classic examples of just absolutely terrible environmental disasters associated with oil spills. We don't take into account environmental costs when we make the market price. And as a fossil fuel, we release a significant amount of CO2 from the burning of those petrochemicals, as well as a series of other air pollutants that we'll look at in Unit 7. And then this idea of international supply interruptions or disruptions is something to think about when we rely on oil. The United States, in order to respond to OPEC's control over the global market, as well as Canada and a couple other countries, have shifted to other sources of oil other than conventional. Tar sands or oil sands is a mixture of clay, sand, water, and what we call bitumen, which has, a fair amount of net energy within it. The ratio is not as nice or not as great as conventional oil because of the extraction process, but we do have some available to us. So much of this comes from North America. A lot of the tar sands comes from Canada, and the oil shales come from the central United States. But the impacts on land, air, water quality, wildlife, climate are really severe. So basically in Russia or in Canada, they'll have to clear whole paths of boreal forest in order to expose these tar sands. As they do that, they emit a significant amount of air pollution. And then to refine the sands and basically withdraw the actual petrochemical materials from the sand that they want, it requires a lot of pumping of water, and the excess water is going to pollute basically nearby water resources and generate this toxic sludge material. The other thing that the United States tried was to shift to accessing oil via shale. Shale is a oil-containing and natural gas-containing rock layer, and we have a fair amount of it in the United States. It's hard to access. It's not as easy to access as liquid oil, crude oil. It's a material called kerogen, and it has to be heated and then refined in order to obtain the actual liquid shale oil. But we have a large source of it in the US, but because of the extraction process, it has a lower net energy yield. But the United States, or companies in the United States, geologists and engineers thought this was a great idea because it allowed us to compete on a world market with OPEC in a way that we hadn't before. And so it was a push towards doing this when OPEC's prices were super high in order to give the United States and the market a little bit of an edge comparatively to OPEC. Along with shale oil is also found natural gas, and this is a mixture of gases, most of which is methane, but they have smaller other lighter hydrocarbons like propane, butane, etc. And there's a pretty high net energy yield from it. And conventional natural gas is often found either above a crude oil reserve or above a shale oil or something of the sort. So there's a gas-rich shale, and if you dig down, you can actually reach that natural gas pocket. Sometimes the gases are cooled and liquefied to be removed at a very high pressure. And we refer to this as liquefied petroleum gas, or LPG, and then they're sort of stored in tanks, and the gas can then be moved through pipelines for distribution. The gases themselves can be converted to liquefied natural gas, or LNG, using really high pressures and really low temperatures. And this was done when the OPEC prices were just really high, and the United States was like, yeah, we can really use natural gas as a resource to compete on the world stage. And they built these huge ports where I grew up outside of Boston. These liquid natural gas storage ports were built offshore, and they were supposed to, be sort of the next step in the energy industry here in the United States. But OPEC, in response, dropped their prices and bottomed out the market, and natural gas took a lot longer to actually come into ease of use, which it's now being, incorporated into the market fairly well. But there were a lot of companies that were hoping that this would have happened, 10 years ago, as opposed to what they're seeing right now. Advantages is there's a fair amount of supply of natural gas, and it has a high net energy yield. It emits less CO2, so it is considered a little bit cleaner than other fossil fuels. But when you liquefy it to transport it, it's hard. Basically you have to put in a ton of energy in order to liquefy it to transport it, and because of that, it lowers the net energy yield overall. And there are still some CO2 emissions associated with natural gas. But we're seeing it used a lot more, and it's certainly being used a lot for electricity generation throughout the United States. And we see a lot of natural gas and oil being extracted in the central parts of the United States, which can be associated with fracking. So both these petroleum reserves and natural gas come from mostly marine sediments from hundreds of millions of years ago. And today, here's a nice pocket of trapped oil and trapped gas in a shale. And so to access it, we've got some new technologies. We were able to start drilling horizontally in order to access what we need. And we were able to start doing what we call fracking, or fracking, which basically sends out a liquid slurry material that's like water and some chemicals in it and sand to break apart the shales, because the rock is basically layered really finely on each other, and you can crack those rocks and make space where the oil and the gases will pool. And then you extract them and basically reverse the pressure and pull those materials up and out. The problem is there's a lot of waste associated with this, right? Slurry can bring back with it these salts, these heavy metals, these even radioactive materials from the rock. And once you bring that slurry back up and pull the oil and gas that you want out of it, what do you do with that water? In some cases, you can reuse it. In some cases, it gets stored in wastewater storage ponds at the surface. In some cases, it gets pumped back down and stored in underground wells. Or in some cases, it actually is transported to the nearby wastewater treatment plant. Although those plants typically can't deal with the amount of contaminants that are in it. So the EPA is currently considering some regulations on what we can do with the hydrofracking waste material, but that's still being determined and still being debated at the federal level and at the state level, where these types of extraction processes are going on. Coal is an entirely different beast. Unlike the resources of petroleum and natural gas, coal doesn't necessarily come from ocean sediments. Coal comes from lots of volume, basically, of organic material, mostly based in plants, that have layered over millions of years to create bituminous coal. It's the stuff that we burn. So it has to have been under intense heat and pressure, and it had been a volume and millions and millions and millions of compressed hydrocarbons over the years. It is found in ample supplies around the world because all you really need to make coal happen millions of years ago is high productivity in the plant species on land. So we find coal stores and coal reserves on every continent, and in high quantities. It's there. It's used to generate about 42% of the world's electricity. We're shifting away from coal here in the United States, but in countries like China and other nations, it's still used highly. And it's really good to burn for energy. It is the high net energy yield. But the environmental costs are extreme. It's the dirtiest of all the fossil fuels, meaning it produces the most CO2, but also the most sulfur oxides, the most excess soot and other particulates. It results in the release of mercury and even radioactive materials during the burning of coal. The downsides, other than that, include a lot of disturbance to extract it, right? We have subsurface mining, but we also have open pit mining that's associated with coal stores. And once we've burned it, we have leftover ash, and it tends to contain a lot of radioactive things, a lot of mercury. And so how we store that ash or how we treat that ash is difficult, right? Because it's so toxic, it can run off and enter local water streams. In order to move away from coal or to make coal quote-unquote cleaner, the coal industry started converting coal into what they call synthetic natural gas. This was to clean up coal, quote-unquote, to reduce the amount of air pollution that coal as a fossil fuel produces. But by producing a natural gas from this solid material, you basically lower its net energy yield significantly. Because you have to go through this process to bring the hydrocarbons into a gas form. And so SNG, or synthetic natural gas, sounds nice in theory because it's cleaner on the burning side, but the amount of energy put into that product lowers its net energy yield significantly. So I don't personally think synthetic natural gas is something that is sustainable, but it's being tried around the world as a cleaner version of coal. You should know for the AP exam basically how a coal burning power plant works. I grew up in Rhode Island, and we had a coal burning power plant much like this. And sometimes you'll see these sort of massive cooling towers and people will be like, oh, that looks like a nuclear facility, but in fact it's a coal burning facility. This is the layout of one from Georgia, where you bring in coal reserves that you have extracted. You burn that material in a large boiler. And the waste from that is ash, which is going to, in this case, go out and deposited into a disposal pond. But what are we boiling? We're boiling water from the nearby river, which goes through a series of pipes and is boiled, creating steam. We generate steam, which is going to spin our turbine. As our turbine is spinning, it's spinning a power generator, and that generator is going to send electricity out to a transformer and out to basically transmission lines to be sent somewhere else. What's happening to the steam as it's powering that turbine is that air mass is now cooling. As it cools, it condenses. And when it condenses, we have a lot of warm water. And instead of ejecting that warm water right out into nature, we usually use a cooling tower to cool that water down so that it has less disruption on the local water system. So the cooling tower is going to allow you to cool the water. And in some cases you can reuse that, or you can put that water back out into the river. This precipitator would collect excess burnt material that goes up, but some of the burned material, is going to leave the plant entirely and go up the stack, and that's CO2, other gases that are created, some soot particulates, sulfur oxides, etc. All of those things are going to be released by the power plant, but something like a precipitator might be able to remove some of that from the air before it leaves the plant. So in that case, we can make coal a little bit cleaner, and so we see precipitators like this being installed in coal plants around the world. Nuclear energy works in much the same way. Engineers love to boil water in order to generate electricity, but how we boil that water is a little bit different in this case. In the case of nuclear fission, we are going to basically knock a neutron into our atoms, and that's going to allow that atom to release more energy because we've split that atom. And so in this case, we're using uranium, but there are some plants that use plutonium, etc., etc. All of this is done in a reactor so that we have some control over this process. And we have to do a fair amount of mining and refining of ores that contain radioactive material before it's held in enough refined concentrate material that it's going to be worth using as a power source. So when we mine something like uranium, we refine it and we pack it into what we call fuel rods. Those rods are actually going to go into the fuel assembly in the core of a reactor. And when we've gone through a serious refining process of our uranium ore, a single pellet-sized piece of uranium-235 has about as much energy as a ton of coal. So the trade-off here is great, right? This is going to be a much more energy efficient material. The cost for building a nuclear plant is much higher, and we have to have a lot more control over the release of the energy. So let's sort of walk through the reactor, because it's very similar to this one, where we're doing the burning, but this process where we're actually releasing the energy from the uranium needs to be really, really controlled. So we are going to have a core that is going to be full of fuel rods, radioactive uranium-based fuel. It's really well refined, it's really concentrated, it has a ton of energy, potential energy, that can be released. So when we release that energy, we are basically creating other neutrons, so we need to absorb those neutrons in order to regulate the rate of fission that's going on. And a lot of excess waste heat is produced. So we're going to pump water from our nearby lake or river up into the reactor. That water will actually flow over the fuel rods and pick up thermal energy as it does that. And that steam that's generated when we heat the water is going to again go into a turbine where it spins. As it spins, it's attached to an electrical generator, which generates electricity and sends that out to the grid. As that steam is spinning the turbine, it's losing its potential energy. That steam condenses into water, and that warm water is pumped to some sort of nearby cooling tower. Some of that water can be reused and go back into the condenser, get pumped back into the reactor, and go through the process again. This containment structure needs to be really strong. It needs to be really specific in order to keep the radioactive materials inside. Basically, in case there's a meltdown, in case there's a leak, etc., etc. We don't want that containment structure to be compromised. And so because of the cost of this part of the plant, right now, sort of the average cost around the world is about $14 billion that needs to be invested in order to generate a normal-sized nuclear power plant. So unlike the coal plants, which are fairly cheap to produce or to build, the nuclear plants aren't so much. But the trade-off is here, right, that we have much more potential energy held within a small amount of uranium than an entire ton of coal that we would have to mine. The nuclear fuel cycle is the term that refers to the entire cycle of the extraction of the ore, the enrichment and the refining of the ore, the producing of the fuel rods, the actual production of power at the nuclear plant. And then once the fuel rods are spent, we have to basically store them because they're still really radioactive and they can't be exposed to people, to nature, etc. And in the 1950s, when nuclear power really came online, this was thought to be the future of energy. But it's really, really slow growing. There's a lot of reasons for that. The waste that's produced, we don't really have a consensus for how it can be disposed of. It's not a recyclable waste in any real sense, because it can't necessarily be used again. You could, I suppose, re-refine it and use what's left over. And we do that in sort of a reprocessing facility where we reprocess uranium and send it back and re-enrich it. So there is somewhat of a cycle. But the other material that's produced, the other sort of atoms that are produced at the end, are no longer useful, right? They don't have any radioactive energy for us to use, and so that material needs to be disposed of. There's a lot of public concerns that come with nuclear power. The word NIMBY comes up in this case a lot, where people love the idea of clean energy, but not in their backyard. So nobody wants to live near or allow a nuclear power plant to be established near them. I think your book talks about sort of Chernobyl or other recent, relatively speaking, examples where the containment structure actually collapsed. But those risks are fairly minimal, so to speak. But I think the perception of those risks maintains and is passed through the public. And so the public concerns, I think, remain very high. So overall, for nuclear energy, very low net energy costs, unfortunately, and produces all this radioactive waste. Some environmental scientists and political scientists say that nuclear fuel promotes the spread of nuclear weapons. I don't know if I agree with that, although there have been some cases in some countries that claim to be using their nuclear fuel resources for power when they've really been using them for weapons. So there is some correlation there. But it's got low environmental impacts. It emits far less CO2 than coal or other fossil fuels. And as our technology increases, the risk of accidents is fairly minimal. The wasted material needs to go somewhere. Right now we cool that material in pools, and once it's cooled we transfer it to these barrels, these dry storage barrels, and it's buried. That's kind of the process right now, and once we bury it, we leave it there. It's still fairly radioactive, so we have to bury it to make sure that we don't have that exposure. But, we bury a lot of our wastes. That's not all that surprising. Yucca Mountain is a project that was abandoned, even though we were storing a fair amount of nuclear waste there, because of the potential for earthquake disaster. And we have to store it for thousands of years in order for it to reach its less radioactive state. Just for a statistic, 10 years after being removed, a fuel rod assembly still emits enough radiation to kill a person standing 1 meter away in less than 3 minutes without protection. But if we have the right protection, if we bury it in the right location, we can prevent that radiation from doing harm. And last but not least, a potential renewable source, which will lead us into the renewable question, is fusion. Fusion technologies are being researched. There is no reliable source of energy generation from fusion at the moment, but we're still researching this. Less risk of damage being associated with it. So yeah, we're still considering this as an option on a small scale. And your textbook doesn't go into much detail about it because it's such a new technology. All right. That's it.